Hi there. In this video, we will gonna see an example on how to find eigenvalues and eigenvectors of a 3x3 matrix. In general, when you want to find an eigenvalues and eigenvectors of a 3x3 matrix or a larger matrix, like in general for n by n matrix, you have to follow three main steps. Step one is to find the characteristic polynomial, which is basically the determinant of the matrix A minus lambda times identity. Step two is to find eigenvalues as roots of the polynomial, the characteristic polynomial you found in step one. And in step three, you find eigenvectors by solving the homogeneous linear systems of the form A minus lambda times identity times the vector V being equal to vector 0. And in these homogeneous systems, lambda is actually the eigenvalues you found in step 2. For more information on how and why we have to follow these three steps, I encourage you to watch my video on introduction of eigenvalues and eigenvectors. All right, let's start with step one for this matrix. So I want to find the characteristic polynomial, so I need to form the determinant of A minus lambda times identity. All right, so if this is matrix A, then A minus lambda times identity is going to be this matrix. So A minus lambda times identity is going to be lambda 0, 0, 0, lambda 0, and 0, 0, lambda, which is going to be the matrix minus lambda 0, negative 2, then 1, 2 minus lambda 1, and the last row is going to be 1, 0, 3 minus lambda. So I want to find the determinant of this matrix, negative lambda, 0, negative 2, 1, 2 minus lambda, 1, 1, 0, 3 minus lambda. Just pay attention that this is another way of writing determinant, right? This vertical lines actually shows the determinant of a matrix, right? So to find the determinant of a 3x3 matrix, you have two techniques. The first technique is using the Saros technique, and the second technique is to use the cofactor expansion along one row or one column of the matrix. So the second method is like a more general method that you can use for any square matrix to find the determinant. So I'm gonna just follow that one, okay? So I pick the first row, and I'm going to form the cofactor expansion along that row. So to do that, pick the first entry here, negative lambda, and multiply that by the submatrix formed by deleting the row and the column corresponding to that entry. So lambda is in this row, this column, delete these ones. This is a submatrix. I calculate the determinant of this submatrix. So the determinant of 2 minus lambda, 1, 0, 3 minus lambda, okay? Now move to the next entry, which is 0. So delete the row and the column corresponding to that entry, and then you have the submatrix 1, 1, 1, 3 minus lambda. So 0, the determinant of 1, 1, 1, 3 minus lambda, and then now move to the next entry, which is negative 2, and multiply it by the determinant of the submatrix formed by deleting the row and the column corresponding to 2. So it's going to be this submatrix, right? So it's going to be 1, 2 minus lambda, 1, and 0. Okay, we are not finished yet. So we know that when you're writing the determinant for the cofactor expansion, we have to put some signs here. So if you follow the checkboard, this is going to be plus, minus, plus, right? So I put plus, minus, plus, and then I calculate this, okay? The second term, it has 0 times whatever it is, so I don't calculate it, I ignore it. Now I have negative lambda times the determinant of a 2x2 matrix is going to be the product of the diagonal entries minus the product of off-diagonal entries. So it's going to be the product of 2 minus lambda times 3 minus lambda minus 0, right? This is 0. And then plus, this should be -2, plus -2 times the determinant of this submatrix is going to be 0 minus the product of diagonal entries. All right, so this is going to be negative lambda times 2 minus lambda, 3 minus lambda, and then negative times -2 is going to be +2 times 2 minus lambda. Okay. Look at these two terms. Here, I have a factor of 2 minus lambda. Here also, I have a factor of 2 minus lambda. So what I'm going to do, I'm going to factor out this term from both terms here and here. So I get 2 minus lambda times, so from the first part here, this term and this term left, so I've just put it down here, negative lambda times 3 minus lambda, and from this one, this term left, right? So +2. Okay, now I can simplify this term and expand it, so I get -3 lambda plus lambda squared plus 2, right? And I can rewrite this as lambda squared minus 3 lambda plus 2. So this is a quadratic equation, a quadratic polynomial, sorry, right? And for quadratic polynomial, you can find the roots or you can factor it out in two different ways. The first one, use the quadratic formula. And the second one is to look for two numbers such that their addition is going to be -3 and their multiplication is 2. So what are those two numbers? Those are -2 and -1. There we go. This is my characteristic polynomial for this matrix. All right. So P lambda is going to be 2 minus lambda, lambda minus 2, lambda minus 1. This is the characteristic polynomial. And in step 2, I'm going to set the characteristic polynomial to be 0 to find the eigenvalues. So this one is easy. So set this 0. It means that this term must be 0. 2 minus lambda, lambda minus 2 times lambda minus 1 being 0. So which means that either this term must be 0 or this one, right? So if I set this term to be 0, I get lambda to be 2. Similarly, if I set this to be 0, I get lambda to be 2. And if I set this one to be 0, I get lambda to be equal to 1. So the eigenvalues are basically 1 and 2. This is 2 times, like I have eigenvalue 2 twice, okay? All right, let's move on to step 3. So I want to find eigenvectors, and to do that, first I fix an eigenvalue. Let's first pick the first eigenvalue, lambda 1 being 1, okay? So for lambda 1 being 1, I form this linear system, this homogeneous linear system, A minus lambda times identity of the same size as the matrix A times a vector V being equal to 0. This is vector 0, right? So in this case, lambda is 1, so I replace it by 1, okay? So this is going to be, so this matrix is going to be exactly the same as this matrix. This is A minus lambda I, right? Here, I'm going to replace lambdas with 1. So I get -1, 0, -2, 1, 2 minus 1, which is 1, and 1, 1, 0, 3 minus 1, which is 2. All right, so I have this matrix times a vector V, let me call it V1, V2, V3, by its entries, is equal to vector 0. Okay, so to solve this linear system, we are going to use the Gaussian elimination or the Gauss-Jordan technique, right? So we have to form the row echelon form or reduced row echelon form. All right, so first I form the augmented matrix, which looks like -1, 0, -2, 0, 1, 1, 1, 0, and then 1, 0, 2, 0. Okay, I have to pick the first leading term of the first row, which is -1. I scale it, I make it as 1. So row 1 being scaled by -1. So I'll get 1, 0, 2, 0. I just rewrite row 2 and row 3. Okay, now that I have this as 1, I can use it to make the terms under it to be 0, the entries under it to be 0. So I use replacement. So replace row 2 with row 2 minus row 1. So 1 minus 1 makes this 0. Similarly, replace row 3 with row 3 minus row 1. So the result is going to be 1, 0, 2, 0, and then 1 minus 1, 1 minus 0, 1 minus 2, 0 minus 0, and the last one is going to be 0, 0, 0, and 0. All right, so this is the leading entry of the first row. This is the leading entry of the second row, which is already scaled, which is already 1. Everything under it is 0. And there is no leading entry for the third rows. And look at the leading entry again. Everything below and above are 0. So this is the reduced row echelon form, right? And we know that the rows correspond to equation 1, equation 2, equation 3, and columns correspond to variables v1, v2, v3. And v1 and v2, they correspond to leading entries, so they are leading variables, and everything else must be free variable. In this case, v3 is a free variable. So set v3 to be some parameter t being in R. Okay. Now I'm going to use equation 2 and equation 1 to find v1 and v2. So from equation 2, I have 1 times v2 minus 1 times v3 equal to 0. And I know that v3 is t. So I have v2 minus t being 0. So I get v2 to be t. Similarly, I use equation 1. Okay. So I have 1 times v1, 1 times v2. Sorry, I have 1 times v1, 0 times v2, plus 2 times v3 being 0. Replace v3 by the parameter t. So I have v1 plus 2t being 0, which gives me v1 to be -2t. All right, so the solution to this homogeneous system is of this form. So v1 is -2t, v2 is t, v3 is t. I can factor out t, and I get -2, 1, 1, right? So t times this vector, and this is the general solution, the solution set for this system, right? Which is exactly the eigenvectors corresponding to lambda being 1. There we go. So in particular, if you set t to be 1, this vector is an eigenvector. You can set t to be anything. So you have like infinitely many eigenvectors for this eigenvalue, and you can just change t to be anything. Okay. All right. Now we found eigenvectors for the first eigenvalue. We move to second eigenvalue. So for lambda being 2, I repeat this step. I repeat step 3. Okay. So again, I form a minus lambda times identity. So I get a minus 2 times identity times vector v equal to vector 0. So if I write this down, I get -2, 0, -2, 1, 0, 1, 1, 0, 1 times v1, v2, v3 being equal to vector 0. Okay. Now, I know that you already know how to use Gaussian elimination or Gauss-Jordan elimination. So I'm going to skip the part that I form the augmented matrix and make it as reduced row echelon form. Okay? I'm just going to write down the final solution. So the augmented matrix, -2, 0, -2, 0, 1, 0, 1, 0, 1, 0, 1, 0. And then after applying row operations, the REF, the RREF is going to look like this. So it's going to be 1, 0, 1, 0, and then 0, 0, 0, 0, 0, 0, 0, 0. So this is the RREF. Okay. Rows correspond to equation 1, equation 2, equation 3. Columns correspond to V1, V2, V3. And here, this is going to be the leading entry of the first row, which correspond to V1. Look at row 2 and row 3. They're all 0. So there is no leading entry in row 2 and 3, which means that the other variables are free variables. Okay. So I set V2 to be T and V3 to be some other parameter T. So T and S are in R, right? And I'm going to use equation 1 to find V1 in terms of the other parameters, right? So from equation 1, I get 1 times V1 plus 0 times V2 plus 1 times V3 is equal to 0. I know that V3 is the parameter S, so V1 plus S is 0, which means that V1 is negative S, okay? So I can write down the solution set as, so V1 is negative S, V2 is T, V3 is S, okay? So what I can do here I have two parameters. What I can do, I can write this as negative S, 0S plus 0T, 0. So what's happening here is that I separate the terms with S and the terms with T. Okay, so if you add these two, you get the same vector, right? Now I can factor out S from here. So I get S times -1, 0, 1 plus factor out T from the second vector. So T times 0, 1, 0. There we go. This gives me the eigenvectors corresponding to eigenvalue 2. Okay, so in particular, if I set, for example, if I set S to be 1 and T to be 0, what's happening is that I make the whole term here to be 0. So I get V to be -1, 0, 1. So this is an eigenvector corresponding to lambda being 2. Okay? Again, you can set S and T to be any parameter in R. You will get different answers. But the point is that all of them are eigenvectors corresponding to lambda being 2. So this is eigenvectors of lambda being 2. All right. So that's the end of the example. But before I finish the video, I want to say something. I want to point out something really important about finding the roots of the characteristic polynomial. Here it was easy because I could factorize these terms of degree 1 in the characteristic polynomial, and so when I wanted to find the roots, I could easily just set these terms to be 0 and find the root. Okay, what if that's not the case? What if you have a polynomial of degree 3 or a polynomial of degree 4 and you don't know how to factorize it, how to find the roots? In general, you don't have a fixed formula to find that, but there are like some tricks, and the important one is the one I'm going to tell you about. So suppose that you have a polynomial of degree n, such as lambda to the power n plus c1 times lambda to the power n minus 1, and so on. So the constant term is cn, and you want to set this to be equal to 0. In other words, you want to find the roots of this degree n polynomial in terms of lambda. So we first look for integer solutions usually when you want to solve these kinds of equations. And in fact, all the integer solutions must be divisors of the constant term Cn. Let's see this in the example we just did. All right, so let's say I calculate the characteristic polynomial up to here, and I didn't notice that I could factor out these two. So what we usually do, we just try to expand this term, add them together, right? Let's do that. So here I have negative lambda times, now multiply this term by this term, so 2 times 3, 2 times negative lambda, and then negative lambda times 3, negative lambda times negative lambda. So I get negative 3 lambda plus lambda squared, and then multiply this to the parentheses, you get 4, and you get negative 2 times lambda. And again, go back to this one, multiply negative lambda to everything here, okay? So what you eventually should get is negative 6 lambda minus lambda, which is going to be plus 5 lambda squared, minus lambda cubed, plus 4 minus 2 lambda. So if you just multiply all this, you will get this part, and then I just repeat this part here, okay? So I can rewrite this as negative lambda cubed, write this one, and then plus 5 times lambda squared, negative 6 lambda, negative 2 lambda, negative 8 lambda, and then plus 4. There we go. And to make things easier, I'm going to just factor out negative sign from the largest degree. So it's going to be lambda cubed minus 5 lambda squared plus 8 lambda minus 4. All right. So suppose that you got this characteristic polynomial. Okay. How can I find the roots? I'm going to look at the constant term, which is negative 4, and I'm going to find the divisors of negative 4. So the divisors of negative 4 are basically plus or minus 1, plus or minus 2, and plus or minus 4. Let's start with plus 1, okay? So if plus 1 is a root, it means that if I just plug it in, I should get 0, right? So basically, I'm finding like 4, lambda being 1, I'm finding p of lambda, or p of 1. So it's going to be negative times 1 cubed minus 5 times 1 squared plus 8 times 1 minus 4. And if you calculate that, this is going to be exactly equal to 0. So if you get the polynomial to be 0, it means that plus 1 was a root, okay? So now I found the root. What I'm going to do, I'm going to divide the polynomial, the characteristic polynomial, lambda cubed minus 5 times lambda squared plus 8 lambda minus 4. I'm going to divide it by lambda minus 1. So if lambda equal to 1 is a root, then I should have the factor of lambda minus 1 in the characteristic polynomial. So here, if I want to divide, consider the term with the largest degree here, the term with the largest degree here. You want a term to multiply it by lambda to get lambda cubed. So it's going to be lambda squared, right? So I'm going to write it down here. Lambda squared, okay? Multiply lambda squared by this. So lambda squared times lambda gives you lambda cubed. Lambda squared times -1 minus lambda squared. Subtract this from the characteristic polynomial. So these two cancels. And then this minus lambda squared gives you -4 lambda squared. And then you just put everything down here. Repeat this step for this one, for this polynomial. Pick the term with the largest degree. You want to multiply lambda by something to get -4 times lambda squared, which is going to be -4 lambda, right? If you multiply -4 lambda by lambda, you get -4 lambda squared. -4 lambda by -1, you get +4 lambda. Subtract these two, so this and this cancel out. 8 lambda minus 4 lambda, you get 4 lambda, right? I'm going to rewrite everything here. So I get 4 lambda and then -4. All right, almost there. Now, again, look at the result. Take the term with the largest degree, which is 4 lambda. You want to multiply lambda by something to get 4 lambda, which is going to be +4. So it's going to be +4. Multiply +4 to lambda -1, you get 4 lambda -4. Subtract these two, you get 0. This means that you can write the characteristic polynomial as these terms times this term. So you get it as lambda -1 times lambda squared -4 lambda +4. Okay, things get a little bit easier. Now here you have a degree 2 polynomial. Look for two numbers that their addition is -4, their multiplication is 4, and those two numbers are -2 and -2, right? So I can rewrite this part as lambda -2 times lambda -2. Just bring this down. There we go. This is the characteristic polynomial. This is exactly similar to what we had here. Just don't forget here I had a negative sign. I can bring it down here and here. It doesn't change the root, okay? So there we go. That's how you can find a characteristic polynomial in general for a polynomial of degree 3, 4, 5, and so on.